All right. Folks at home, you can hear me okay? Yeah? All right. Let me turn down the lights here in W112. I will say, Zoom refugees, we have plenty of space here in W112, so if any of you are dying to come to class and... Oh, the screen is screwed up for folks. All right, let me try to stop sharing again. Dun, dun, dun. Can you see the screen now, folks? Is it weird, folks at home? Fixed. Okay. Please let me know if you still have trouble. All right, so I guess we're good to go. I was saying that we have plenty of room in W112, so folks at home, if you're interested in coming to the classroom, you can pretty much come whenever you want. If you're comfortable staying home, then that's fine too. All right, last time we were talking about nomenclature. I warned you about the pitfalls of, but what if the molecule were more complicated? An example of something I told you I didn't care about was numbering of molecules. Oops, I want to be on a different screen. And the reason we don't care about that is that numbering itself is important. However, the choice between two alternative numbering schemes for a molecule may not be important. So this is an example, I think, that comes from either a study guide or a practice exam. And I'm sorry if some of you have seen me talk through this already in office hours, but I thought it was useful enough that other people would benefit from it. So as I look at this molecule, if I identify the longest chain in it, it's 7 carbons. Now this doesn't have some highest priority functional group in it. It's just an alkane with a chloride in it. So this is going to be named in the suffix with hept to indicate 7 carbons. There's going to need to be a chloro in the prefix and a methyl in the prefix to identify these groups. What? 1, 2, 3. No, there are 7 there. That's called gaslighting. You should try it sometime. Is that better? There are 7 carbons there now, I think. Are we okay? All right. I don't endorse gaslighting. It's a cruel thing to do. So the question becomes, and then we're going to need an ene at the end of our name to account for the fact that we've got a double bond there. Now, numbering. What are we going to do for numbering? Well, we could number starting at this end, 1, 2, 3, 4, 5, 6, 7, in which case this would be 3 chloro, 5 methyl, hept 3 ene, where the 3 could either go here or there, and we don't really care. Alternatively, I suppose you could say, well, what if I want a number in the other direction? Fine. Not sure what color to choose, whatever. 1, 2, 3, 4, 5, 6, 7. Oh, well, we could choose 3 methyl, 5 chloro, 4 hept 4 ene. All right? I don't care about either of those options. I mean, either of them you could use to draw the structure unambiguously. So it turns out to not matter as far as I'm concerned. Now, what you would need, though, is to identify the configuration of that double bond. Unless you have some information there, it's impossible for someone to draw the correct structure. But as I said, on a question, I would accept either numbering scheme. Not really important. Yeah.
Does it matter which prefix you put first? Like if you say 5 methyl 3 chloro, or
Yes, does it matter which prefix you put first, 5-methyl versus 3-chloro? Technically, yes. In reality, I don't care. And it would be kind of, I mean, just think of it in terms of a test-taking strategy, or I'm the games maker from the Hunger Games or whatever, and if two of the options are 3-chloro 5-methyl versus 5-methyl 3-chloro, guess what? You guys can pretty much guess what the answer to the question is. So that made it sound like I'm evil and trying to trick you. Let me back up and just say that, yes, you're supposed to do it in alphabetical order, but no, it doesn't matter. As long as your name has all the information in it you need to draw the structure unambiguously, you're fine. And then also understand, on a multiple choice exam, you're not going to be writing names from scratch. You're going to be choosing from options. All right. All right, so let's talk about how to assign configuration of the double bond. I'm looking at the chat on my screen, and I can't read and talk and draw at the same time. So any other questions of how we did that? Go ahead.
Yeah, so is there no highest priority? Is the double bond the highest priority?
What is the highest priority group here? I think your list says chloro is never the highest priority, and so the highest priority group is probably, the double bond in the long chain. That's probably the best you can do. I suppose we could make it more complicated, and if we wanted to put a ketone there, then we would have to name this 2-one at the end of it, and then that would actually make our numbering choice easier, because you're supposed to number in a way that gives the highest priority group the lowest number. A question from the chat is, how do you know that the methyl group is not part of the chain? If you number to the methyl group 1, 2, 3, 4, 5, 6, you only got 6 carbons. If you number the other way, you get 7. So I suppose that some of you might say, well, can't you just then say, well, this is a 5-ethylhexene? Okay, fine. Again, the standard is, does the name you give it unambiguously communicate the structure? All right, so let's now, did I miss another hand? All right, so you will be tempted in your preparation for the exam to spend an inordinate amount of time doing nomenclature problems. Probably not worth that. The thing that you should work on is, because there will be one or two nomenclature questions on the exam, but you probably should worry about assigning E and Z configuration to alkenes. All right, so let's talk about that. And I think probably to facilitate our discussion, I'm going to need to color some things in. And so I'm going to erase everything that we did above on this structure. Now, hopefully you've read in the study guide, so this is not going to be new to you in terms of assigning E and Z configuration. Remember that when you have an alkene where one or both of the carbons has 2 non-hydrogen things attached, cis and trans may not work for you. A little bit of lingo that's not absolutely essential, but will help you to understand what on earth I'm talking about when I speak. This alkene, which has all hydrogens on carbons 1 and 2, we are going to call it unsubstituted. None of the hydrogens have been substituted for something else. If one of those things, if one of those carbons has only one group, we replace only one of those 4 with one non-hydrogen group, it's called mono-substituted, except we can't spell. If the alkene were like this, it would be tri-substituted. And if it were this way, it would be tetra-substituted. So for unsubstituted or monosubstituted alkenes, there's no stereochemical issues, no E or Z. For disubstituted, you can assign E or Z, or you can assign cis or trans in most cases. For tri and tetrasubstituted, you're going to need E and Z exclusively. Cis and trans isn't going to work for you. All right, so how do we assign configuration? And it helps to just think about conceptually dividing the double bond and considering the groups attached to carbon 1 versus the groups attached to carbon 2. Maybe the squiggly line isn't necessary. So we need to, for each of these carbons, assign which is the higher priority group, which is the one we care about most. This is a detailed competition with rules that are specified in the IU Pack to help resolve any controversies and tie-breaking issues. I lost my train of thought because I looked at the chat. Oh well, it's very sad. Anyway, so let's consider the two groups that are attached to the carbon here, carbon 1, chloro versus carbon. You just look at the atom. It's an atom by atom comparison. So our first round of comparison for carbon 1 is chloro versus carbon. Chloro is heavier in terms of atomic number, so the heavyweight wins and we have our highest priority group. Easy, no problem there. On carbon 2, we do the same comparison. We compare the two things that are attached to carbon 2, atom by atom, carbon versus hydrogen. I mean, maybe I need to oops, that's kind of large. Highlight those two groups so you know which ones we're talking about. Hydrogen versus carbon. Is there a difference? Yes, then heavier one wins, so the carbon-containing group is the higher priority one. Right? At that stage, assigning stereochemistry is easy. If the two hot priority, I used Hannah's pun. Hannah in office hours said something about E and Z not being very easy, so I'm using it again. It will get old by the end of the class. It's already old actually now. So assigning the stereochemical configuration is straightforward. If the two high priority groups on either carbon are on the same side, we call it Z because they're on the same side as each other. And if they were on opposite sides, we'd call them E. All right? So that was a fairly simple one because we didn't need to go through a tiebreaker procedure. But maybe we should. So anybody want to ask a follow-up question there before we go on to a more difficult one?
You're worried about the sigma bonds there, not the pi bonds? Because on number 2, aren't there two carbons attached and then one hydrogen?
Yes, I suppose you, well, hold on. On carbon 2.
So we're not counting, so when you're...
Yes, in distinguishing the two carbons of the olefin, I'm sorry, I used a term there that's sometimes chemists and chemical engineers call alkenes olefins. That's they're equivalent terms. Olefin maybe sounds easier to say. In any case, yeah, the fact that either of these carbons is attached to another carbon is going to be the same no matter what alkene you're in, and so because that doesn't vary, we don't worry about it.
Okay.
Yep. Good question. Anything else? All right. So yeah, for this molecule, you would just, if you wanted to name it, in front of the 3-chloro-5-methyl 3-hept-3-ene-2-one, you would put a Z. And you would put it in parentheses. If there were more than one double bond, you'd put the number in front of the Z as well to indicate which double bond you're talking about. If you happen to put the 3 there and there's only one double bond, it's technically not necessary. But if you put it there because you like to have redundant information, that's fine too. All right. So maybe let's do a couple other sort of strange examples. I'm trying to come up with some from the practice exam. So I'm not even sure if this is a thing. Actually, it is, because Dr. Castle's lab makes amino acids of this kind. Okay, so it's real. Let's go ahead and assign stereochemical configuration. We're not going to worry about what the name of this thing is, but let's worry about E and Z, about the alkene. So just arbitrarily call one carbon 1 and the other carbon 2 so we have something to talk about. On carbon 1, we have our round 1 fight is nitrogen versus carbon. Atom by atom comparison, nitrogen is heavier than carbon, nitrogen wins. Now this allows us to illustrate a misconception that sometimes people make, which is they mistake largest atom for largest group. And they might say, oh, well, here I've got a C, an O, an O, and an H, whereas here I only have NH2, and they try to assess the size of the entire group. It's a reasonable thing to think about, but that's actually not how the procedure works. It's an atom by atom comparison. As you start out, you only consider the 2 atoms that are attached to atom 1, and only if they're the same do you start doing tiebreaker procedures. So for right now at this stage, the rest of this stuff doesn't matter, just the identity of the atom, okay? So it doesn't matter that technically carbon plus 2 oxygens plus hydrogen overall weighs more than NH2. That's not the procedure. The procedure is the atom that's attached. Does that make sense? Okay. So over on carbon 2, it's a bit trickier because as we compare those 2 atoms, they are both carbon. So round 1 is a stalemate, carbon versus carbon. Not sure what to do there. So the tiebreaker procedure, or perhaps the recount procedure, is to consider the things that are bonded to each of those carbons. All right. To facilitate our discussion, we'll call this carbon A and carbon B. Carbon A is bonded to what? Well, it's bonded to 2 other carbons and then 2 hydrogens, which are implied but not shown. At this stage, it will be critical for you to remember the hydrogens that are there that we're not drawing because we're in too much of a hurry. If you forget that, you may miss some things and make a mistake. In contrast, carbon B is bonded to 2 carbons and 2 hydrogens. Okay, another split decision. In order to break the tie, actually, you go down the list one by one. You write your list from heaviest to lightest, and then you go down it one by one. Can carbon beat carbon? No. Okay, hydrogen can't beat hydrogen. Hydrogen can also not beat hydrogen, so we have another tie. And so we have a second tiebreaker procedure, a tiebreaker for the tiebreaker, or a recount of the recount. We move out 1 atom on the chain, and we start over. So we move out this direction and this direction. Now, in this case, there's no choices of which direction to move. Somebody always asks, well, what if you had a choice? What if there were something else here. And I can't think of an example where that would be the case, but if it is, you choose to move out in the direction that gives you the best possible chance of winning. So the second tiebreaker procedure is move out one and then repeat. So we'll call this round 2. You compare the 2 atoms that are attached, carbon versus carbon. Again, it's a tie, so we go through the tiebreaker procedure. And that is enumerate the things that are bonded to those 2 carbons. Here it's 2 carbons and 2 hydrogens. Here it's 1 carbon and 3 hydrogens. So we'll call this one, I don't know, B prime and A prime. This is getting really kind of ridiculous. CHHH versus CCHH. Carbon versus carbon here, it's a tie. Carbon versus hydrogen, at last we have a winner. That is the higher priority group. So automatically, this is the group that we care about. And so we would call this double bond E. All right. Yes?
So are the carbon, so in the round 2, your carbon versus carbon, that's going to be your A prime, your B prime, that's your...
That's right. I'm sorry about that. I guess we should have, hold on, I'm going to make this a little bit easier. Round 2, A prime is carbon, B prime is also carbon. Split decision, then you do the tiebreaker again. All right? And if it was a tie here, you would continue to move out on the chain until you found a difference or until you showed that the 2 things were identical. If they are identical, then you can't assign E versus Z. Remember, I told you that if you draw that, if you've got 2 of the same thing attached to the same carbon of the alkene or olefin, there is no E or Z stereochemical configuration because there's only one way to draw that molecule. If you give this the name 2-methyl-2-butene, that's all you need to get the right structure every time. And maybe you can play around with that to convince yourself that that's the case. But your easy out is if you demonstrate that the 2 things attached to the alkene are exactly the same everywhere, then there's no need to assign E versus Z. All right. Somebody's confused. Why is this alkene Z? E. It's E. Why is it E? It's E because on carbon 1, the highest priority group is nitrogen, and on carbon 2, the highest priority group is this group at the bottom. And the way we decided that was by this exhaustive tie-breaking procedure. So yes, E and Z replace cis and trans for tri-substituted and tetrasubstituted alkenes. Yeah?
So is that really wrong with pairing? Why would you just pull the carbons along the chain until one of them stops?
Instead of doing this comparison, why don't you just follow the carbons along the chain until one of them stops? Good question. So I'll do another example where that may become important. Is that all right? I don't know. I mean, at this stage, I'm sort of making stuff up. So let's just envision the same situation. Yes. All right. So this is the same molecule, only I've added something. I've added a ringer that will change the outcome of this assessment. So carbon 1 stayed the same. Still, the highest priority group is the NH2 group because in the atom by atom comparison in the first round, nitrogen won. For carbon 2, here's why you can't just move down the chain until one runs out. For carbon 2, your round 1 procedure gives you a tie, carbon versus carbon. So your tiebreaker is to consider the things bonded to carbon A versus B. A is bonded to a bromine, 2 carbons, and a hydrogen. B is bonded to 2 carbons and 2 hydrogens. So if I were focused on carbons alone, I would miss the fact that bromine permanently resolves the controversy in the tiebreaker after the first round, because bromine is heavier than carbon. So now, with that subtle small change, this double bond is correctly assigned Z. E and Z have nothing to do with physical properties in the sense that you could say, well, nothing really changed about this molecule, only you threw in an extra group. It's not like you went in there and rotated it or changed the stereochemistry of the double bond. And I'm saying you're exactly right. E and Z is simply a technical procedure for being able to draw the right molecule. All right? It doesn't matter that this group is still on the same side of the alkene as the carboxylic acid, because that's not, remember, cis and trans tells you things about relative relationships between groups. I could still say over here, this 1, 2, 3 carbon group, this propyl group is cis to the carboxylic acid. And I could say the propyl group is trans to the amine, but none of that is concise enough to be in the name of the compound, and so we use this E and Z method. All right. Yes?
So I saw the study guide also talks about R and S.
Yes.
What's the difference between E and Z?
So R and S, the study guide in chapter 3, I think tells you to not worry about R and S at this stage, though it may appear in some names. We're going to see that stereoisomers in general in chemistry are molecules that have the same connectivity, but a different arrangement of atoms in space. And one opportunity for stereoisomers is these double bonds, because rotation around double bonds is restricted. Another opportunity for stereoisomers is an sp3 hybridized carbon attached to 4 different things. In chapter 5, we'll see that there are 2 different ways to attach 4 different things to a carbon atom. There's a left-handed way and a right-handed way, and we'll call them R and S. And that's, don't worry about that yet. Yeah, forget about it. All right, what else? What point was I trying to make with the 2-methyl-2-butene? Not sure. No, the point I was trying to make there is that if we're going to name these carbons 1 and 2 again, just to facilitate the discussion. Carbon 1 is attached to 2 of the same thing. You can see that easily here because they're just 2 methyl groups. But what I'm trying to say would be true even if there were much larger things attached to that carbon. If you've got 2 of the same thing attached to carbon 1, as you go bit by bit and do the tiebreaker procedure, this one versus this one would be a tie. This one versus this one would be a tie. This one versus this one would be a tie. This one versus that one would be a tie. This one versus that one would be a tie. All the way out, it's the same. You can't assign E versus Z. And in fact, you don't need to. What I was trying to demonstrate with 2-methyl-2-butene is if somebody just gave you that name, 2-methyl-2-butene, you could draw the butene. Oh no, I'm not sure. Is it cis or trans? Well, actually it doesn't matter, because once I put a methyl group there, it could have been either one. Maybe that one was the first one I put, and then I added that one. See what I'm saying? The 2-methyl-2-butene completely tells you what you need to know about that molecule. Go ahead.
Just to make sure I'm understanding, so Z is when they're both on the same side, and E is when they're split.
E is when they're on opposite sides. Z is the same side. All right. I missed a hand over here? No? Okay. All right, so that's worth some practice. And there are plenty of examples. You need to, let's see. Like King Benjamin, I cannot tell you all the ways or means whereby you may commit stereochemical sin by misassigning E versus Z. But this much I can tell you, that if you don't watch your procedures and rules and atom weights and so on, you will perish on the exam. So remember, O men and women, and perish not. Right? You need to practice this, discover your own misconceptions, make a mistake like I was talking about where you think, oh, the larger group overall wins, because that's not how it works. Do this several times, check your answers, make sure you can get it every time. If you do this, chapter 5 is going to be real easy. I keep saying easy, isn't that fun? If you do this, chapter 5 is going to be more straightforward to do. No, easier is better, because we'll use the exact same procedure to assign R versus S. All right, sorry, go ahead. Do you look like at atomic number or molecular weight? Atomic number, because it's an atom by atom comparison. Yeah. This is a funny quote. I wonder if people are going to get offended if I read their little tweets out loud. If he's preaching as King Benjamin, does that mean he will tell us that we are even as the dirt of the earth? No. You are made of the dust of the earth, but it's interesting in the book. Here's my one spiritual thought. It's for the whole semester. We're just going to do it now, get it out of the way. I may tell you others. Interesting in the book of Moses that Moses learns after beholding the glory of God. First, he concludes, now I know that man is nothing, which thing I never had supposed. But then God tells him that man is everything. And by man, please, I should not use that term. His children, women, and men, because they are his work and his glory. The whole universe exists for them. So, all right. Sorry. No, I don't need to apologize for even awkward attempts at spirituality. Just be glad my kids aren't here, because they'd be rolling their eyes. We try, come follow me with teenagers. I don't know how it is with college roommates. I just haven't been in your shoes, but with teenagers, they want it to be over, but their behavior is such that it makes it longer. Like, if you guys would just stop belly aching and shut up, we could be done with this. But instead, we're having to pause and wait, and then, Adam said this. That was a dumb answer. Poor little Adam, the 10-year-old. He's got these teenage brothers that like to remind him all the time that he's an idiot. I was an oldest son, and I only had a younger sister who was 5 years younger, so it was totally different dynamic, and it's just kind of nuts at our house. But yeah, we sit at the table, we try to read our scriptures, and there's always, why do we have to do it? And I think to myself, well, someday you're going to be parents sitting down at a table trying to get your kids to do stuff that they don't want to do, and then I'll be laughing at you, because what goes around comes around. Occasionally, it's possible that a notification will pop up at the top of my screen with a child requesting something through iTunes. So don't be shocked when I just click denied all the time. Denied. It's really... We're off track. I'm going nowhere. Whew. All right, well, we'll pause for a drink of water. Let me collect my thoughts. All right. There's something else that's really important in chapter 3 that is really more important than nomenclature, and really is the foundation for your understanding of biochemistry and basically life as a whole. And that is the concept of what we will call non-covalent interactions. What do we mean by non-covalent interactions? Well, a covalent bond involves, like we said, mixing of two atomic orbitals to make a lower energy bonding molecular orbital that's filled and a higher energy antibonding molecular orbital that's empty. And this is a covalent bond, and covalent bonds tend to be worth depending on their strength, anywhere between, I don't know, 70 to 105 or so kilocalories per mole. Kilocalorie is a unit of energy. It is a unit of energy that organic chemists by tradition prefer over kilojoules because they can't make me use the metric system. I'm actually pro-metric, except when it comes to calories, because organic chemists were brought up learning to think in calories. The number scale is useful. If you care, there's like 4 joules to a calorie, so whatever. A good rule of thumb, based on the idea that delta G equals minus RT ln K, is that at around 298 Kelvin, or room temperature, if delta G is 1.36 kilocalories per mole, equilibrium constant will be 10. A change in delta G of about 1.4 kilocalories will change an equilibrium constant by a factor of 10. So making new covalent bonds often can lead to equilibrium constants that are huge in the forward direction, and those are the reactions we love because they're really efficient. Non-covalent interactions are favorable, but they are worth much lower amounts of energy. And they are generally considered to be reversible. By lower amounts of energy, we're talking 5 to 10 or maybe 1 to 10 kilocalories per mole. But they are important because, remember, life occurs, at least on this planet, at room temperature plus or minus some number of degrees. And what that means is any individual non-covalent interaction can change a biological process and perhaps even increase its favorability by a factor of 10. And that starts to have enormous consequences. So it's useful to know about these things. Non-covalent interactions are involved in your cell membranes. They're involved in all of the recognition that occurs at the cell surface, molecules binding receptors. They're involved in signaling between neurons. It's all non-covalent interactions. If you want to know how life works, understanding this is really key. And so you've learned about these in general chemistry before, and probably you learned about them in a boring way. Oh, my apologies to my colleagues. I'm sure they didn't teach you in a boring way, but probably I remember not appreciating these and thinking that they were kind of stupid. For example, have you heard of an ion-ion interaction? Have you heard of an ion-dipole interaction? How about a dipole-dipole interaction? How about a dipole-induced dipole interaction? How about an induced dipole interaction? And then actually every place we've got either dipole or induced dipole, we could put ion to. It just looked like we were mixing and matching things, and you were told that they were all weak interactions, and therefore you probably didn't need to worry about them. Well, tell that to the gecko that can walk on walls because of non-covalent interactions. It has a huge, huge effect. Tell that to the researchers at Pfizer and AstraZeneca and Moderna and others who are using nucleic acid technology to invent vaccines, and that's all based on hydrogen bonding and van der Waals interactions. So we'll talk about these, and I'll try to illustrate as we do the significance of some of these interactions. People always ask me, oh shoot, what am I going to need to know? Is this on the test? You're going to need to know it to create worlds someday, and if you don't learn it now, then we'll have to be in a class again up there. You'll be learning it and I'll be teaching it. So let's just save ourselves some time and learn the useful stuff now. And then, yes, there will be some questions on this on the test. All right, so the most basic kind of non-covalent interaction is what some people call ion pairs. I don't really like that term. Some people call it an electrostatic interaction because this is really an attraction or repulsion between point charges. And so this is just Coulombs Law, right? I forget what Coulombs Law is. The energy of an interaction between two charges is equal to charge 1 times charge 2 divided by the radius, and then there's something like 1 over 4 pi times something to do with the medium that they're in. That number actually turns out to be important for reasons we might get to. But so you might expect, Dr. Price, do we need to memorize Coulombs Law? No, because you can look it up on the exam, right? Memorizing stuff is pointless. This tells you that the most important conclusion from this is the interaction is stronger at shorter distances. Okay? Now, you may have learned about something in general chemistry called the ionic bond. And you may have been told ionic bonds are very, very much stronger than covalent bonds because they involve full transfer of electrons. All right? Like Obi-Wan Kenobi, what they told you was true from a certain point of view. Because what they meant by that is that if you take sodium with a positive charge and chloride with a negative charge in a vacuum, and you measure the energy required to separate them in a vacuum to infinite distance, then yeah, that's a huge amount of energy. Whereas if you take a covalent bond, say hydrogen, and you want to separate this in a vacuum to infinite distance where R equals infinity, that's only about 105 kilocalories per mole. But biology, as far as we know, doesn't happen in a vacuum unless you're watching Star Wars Rebels or the Clone Wars, where they have these weird creatures that float in space. They swim in space even though there's nothing to push against, and they can somehow go to hyperspace. Never really figured that one out. In any case, nature, we don't live in a vacuum, and so the relevant comparison point for biology is not infinite distance in a vacuum. So what happens to an ionic compound when you put it in water? Dissolves, it separates. Does that seem like a very strong bond? Well, it's relative to what, right? So in the solid, you have lots of sodium ions surrounded by chlorine ions in a large three-dimensional cubic lattice. And each of the sodium ions and each of the chloride ions is surrounded by other ions, and they're interacting with each other. When you put them in water and wait a while, after a while, each of the sodium ions is completely surrounded by water molecules, and the water molecules orient themselves so that the electronegative, partially negatively charged end of water is pointed towards the positively charged sodium. Do we need to talk about what a dipole is? We're good with electronegativity differences, and you're good with the fact that it's a vector quantity, so water has a negative, partial negative charge on the oxygen. Is that all okay? So what we're doing when we dissolve salt in water is we are replacing all of those ionic interactions with even more ion-dipole interactions. Ion-ion interactions versus ion-dipole interactions. And it turns out that the free energy for a process is related to the change in enthalpy versus the change in entropy. Change in enthalpy you can think of in terms of the strength of interactions slash bonds. Entropy just think of in terms of disorder. When you dissolve salt in water, you're replacing a few ion-ion interactions, which are stronger, with many more ion-dipole interactions, which, though weaker in aggregate, are probably about the same. So in terms of enthalpy, dissolving is maybe a bit of a wash. And I didn't show you here that chloride would be likewise surrounded with water molecules. So I don't want to get in trouble with potential sources of confusion, so I will do my favorite thing, which you guys hate. Is that dangerous that I like to do things that you hate? The copy and paste, because you can't do it in your notes unless you're using an iPad. Shrink. Okay, yeah, so chloride's there too. Thank you. Dang it. It's just bad karma. I went and I was mean, and therefore I was punished. You're exactly right. In chloride, each of the positive end of water molecules should be oriented towards the chloride and so on. I think that'll be enough to summarize the idea. Well, isn't chloro surrounded? Yes, fine. Okay. So in terms of the change in the strength of interactions, it may be dissolving may be a little bit more favorable or a little bit less favorable, but it's probably not a huge change. The big change here is the change in entropy. In the dissolved state, in the lattice state, the ions had a lot of order. They had to be next to each other, and there was only one way to do that. In the dissolved state, there's lots more freedom, lots more disorder. And so it's a favorable process in terms of entropy. Yeah?
So because you're replacing because you're replacing more of a relatively strong bond with a lot of weaker bonds, but you're having a lot of them, and that's making more entropy, that's why it's favorable?
Yeah, I mean, you can measure actually enthalpies of dissolution, of dissolving. You just take something, you dissolve it, and you watch the temperature of that solution go up or down. Some things when they dissolve are exothermic, meaning they release energy and things get hot. Some things when they dissolve are endothermic and they get colder. But the idea, and I don't actually know what that delta H number is for this process, the idea I'm trying to convey is that when you think about whether something is strong or not, strength is always relative to something else. You got to know what state you're comparing it to. Yes, the ion-ion bond pair is strong if your reference point is separated at infinite distance in a vacuum, but if you're talking about separated and solvated in water, not a big deal. Okay? And this is going to be important in a lot of different biological processes. Ion pairs, and I guess that's, dang it, I wanted to do more. I guess that's all we have time for. Chapter 3 study guide isn't due tomorrow. I'll just make it due after the exam, probably Wednesday. Chapter 3 will be on the exam. Chapter 4 looking like not. So, yay. Have a good weekend.